Neural networks are all the rage these days, and for good reason. Neural network computing is taking over a ton of amazing applications like driving our cars, beep beep, hey, watch your... monitoring our security cameras. Look, the system has identified a female engineer getting out of a car with a... Oh, oops, never mind that one. Interpreting speech and voice commands, and beating us at our favorite games. Thanks, AI. Anyway, lots of this artificial intelligence is being done in huge data centers with acres of special processors and piles of power. But what about when we need embedded neural network capability due to latency, safety, security, and a host of other reasons? You don't want your driverless car suddenly losing its mind because it can't find an answer back from the cloud. Left? Right? Where do I go? Kinda need an answer here. Hi, I'm Amelia Dalton, host of Chalk Talk. Today I'm chatting with Pulin Desai from Cadence Design Systems about some new processor IP designed specifically for neural network inferencing. Now you can put the power of AI right into your next SoC with no cloud required. Check it out. And before we get started, don't forget to click that link. There you can find out more information about Cadence Tensilica Vision C5 DSP. Hi, Pulin. Thank you so much for joining me today.
Hi, Amelia. How are you doing?
I am great. Thank you for asking. All right, so we're here to talk about deep learning and neural networks. So set the stage for me. How do you fit into this picture? And you guys have been in the processor and DSP IP business for a while, right?
Yeah, that's correct. Everybody knows Cadence as an EDA supplier, but I am from Cadence's IP group, and within IP group, I am part of Cadence's Tensilica group. Our customerships are close to 4 billion processors a year. We are a number one DSP IP company in terms of revenue. In fact, we are a top choice for audio DSP licensing company, and I am from the imaging and vision group that we license our vision DSP to SoC supplier. And one company that I can mention, MediaTek, licenses our vision DSP for that X30 application processor for the mobile market. In terms of semiconductor companies, out of top 20 semiconductor companies, 17 semiconductor companies uses Cadence's Tensilica processor. So this gives you an idea where I come from and what type of products we provide.
Excellent. Okay, so an important aspect of deep learning and neural networks is analysis, of course. Walk me through the subsystems here.
Yeah, that's correct. So at the end of the day, you want to analyze the data and find out what is inside the data. And that's what essentially a neural network is doing. And then what we are talking about over here is that in a classical embedded system, people use the word called inference, that in a classical embedded system or an edge devices, how does the whole data flow works or how different systems are working. And what we like to call it is that there are three different subsystems that ends up happening. There is a sensing part. The sensing part is what you would call that touches the outside world, the analog world. Then after you have received the data from the analog world, you may do some kind of a pre or a post processing, and after that you may analyze on it. So if we look at the sensing part, there is so many different ways to touch the outside world. So one way to touch, maybe you might look at with image sensors. So this is how we take a picture, or this is how we take video. Another way maybe a radar or a LiDAR, and another way maybe a microphone, or so many other ways to touch and get to the analog world. And once you have captured this data, the next phase you may want to do the pre or post processing, like remove some noise reduction or any kind of a post processing. And then the third phase, once now you have prepared the data, you said, okay, what is inside this data? Can I find an object? Can I find something useful in it? And that's what the analysis part it is. And this is what you would see in all embedded system that we will be talking about moving forward. So what you're looking at it is that I just described these three subsystems. We can actually look at it more a pictorial way here. So in a typical system in a mobile, smart home or surveillance where you might have an image sensor, and the image sensor is what you would call something called a Bayer sensor. And this is a Bayer format. That's what the left-hand side is showing you. What it's shown here is called ISP that converts the Bayer data into an RGB. So that's how you sense the outside world. You convert the analog world into the digital world. So that's the sensing part of it. Then the next phase after that is what you call the post-processing. And in here, you might do some 2D, 3D noise reduction. You might do a high dynamic range conversion. So one example would be that if you have been taking images in a situation where there's a lot of light coming behind you, your face becomes very dark, especially if there is a lot of light. Then when the face becomes very dark, you want to see if you can recover that face, and that's where the high dynamic range processing may happen. Or you might have a stereo sensors, which is what is happening in most of the typical mobile phone. You might do some processing on it, and after that you may send that image to do some analysis. So what would that analysis be? You might detect the face within it. You might see if there is a face recognition that you want to do. So this is a pictorial way of showing how those three blocks that I talked about. And then if we move on to from the actual pictorial way to an actual system where an SoC, a system on a chip, will be designed, where now what I have done over here is this is a typical subsystem where you have a CPU, you have a GPU, memory controller, and I/O. But on the left hand side, you see on the bottom I've shown you a sensing system where a camera system, there is an ISP connected to the image sensor. Then you might have an audio input for audio voice processing and audio voice input. And then on the top in the red, you are looking at a pre and a post processing where you have a video DSP and an audio DSP. And then after those two blocks, the third part is now you want to analyze. And this is where now we are introducing the concept of neural network DSP. So what we are saying over here, and one of the main point that we are bringing over here is that regardless of the input that you are bringing from the outside world, whether it's coming from the camera, whether it's coming from the audio, or whether it's coming from radar or LiDAR, there is a need for a neural network DSP to do the analysis. And that's what is being shown on this subsystem in an application processor for these different markets: mobile, smartphone, a smart home, or a surveillance camera market.
Okay, Pulin, so we talked about smart home, but automotive is also a really big market for sensing systems and neural networks. Do you have an example of what that flow looks like?
Yeah, we talked about the consumer market with the mobiles and smart homes and surveillance camera. But same thing can be in those three major blocks that I talked about. Same thing can be talked about for automotive. And in automotive case, in order to move on to the autonomous car, as we move on to that world, you have the same concept, the radar that you might be using to see the far away. You might be using LiDAR to maybe see the medium range area, and then the camera, the image sensor, and then obviously there's ultrasound. So there are 4 different types of sensors are being used to sense the outside world. So information comes in, you need to do some kind of processing to recover the data. What would you do to analyze? You might want to do some object detection, lane detection using a neural network.
Okay, Pulin, so how does this fit into the SoC system typically?
Yeah, so we talked about an SoC system for a mobile or surveillance or a smart home. The same way we can take a look at how an SoC system would look like in an automotive area. And then if we look at this block diagram, again, the sensing is an imaging system with an ISP. There could be a radar processing system that's looking at the radar. The similar way, it could be LiDAR up there. I have not shown that here, but you can think of that way. And then there is a next block of the post or a pre-processing for a vision DSP that comes from the imaging system and the radar processing. And after that, we are showing a neural network DSP. And then the CPU, GPU, memory controller, and I/O are always going to be there. So again, what we are showing over here is that in a typical SoC, regardless of the input subsystem or a sensing system that you are looking at, a camera, radar, LiDAR, there is going to be a need for a neural network DSP to analyze that.
Okay, so Pulin, within the last 4 years, the computational requirement for neural networks has gone through the roof. Are you seeing that as well? And there seems to be a lot of change happening in this space.
This is an area for tremendous investment. I mean, everybody is making a lot of investment in this area. There are lots of PhDs working in this area. So talking about computational requirement, as you said, yes, last 4 years, we have seen computational requirement increasing up to 16x, and that can be seen by looking at the ImageNet computation, where in 2012, AlexNet was about 0.7 gigamax per image, and in 2015 the ResNet became 11 gigamax per image, and that's approximately a 16x in less than 4 years. And this is in 2015, and that requirement continues to increase. Now, as I said, that there is a tremendous investment being made. Because of that, there is a lot of evolution happening in this area, and a lot of new algorithms or new things are being invented for the neural network. Examples would be in AlexNet, there were bigger convolution. In Inception, there were smaller convolution. These are just one example. And then as we talked about, the neural networks are being used in all the market: automotive, servers, home, mobile, and surveillance. So us being an IP provider, we have a challenging task. We are sitting here in 2017, and we are providing an IP for customers who are developing SoC for 2019, 2020, or in some cases 2021. And they need to provide an SoC that will have to cope with this changing world. They will have to develop an SoC that will work with this increasing computational capacity. So we need to provide them a programmable machine. We need to provide them a scalable machine. And we need to provide them something that's low power, because we are providing a solution for embedded platform and for the inference solution.
Okay, Pulin, now since we're at Cadence, we should probably get into the details of your C5 DSP. So, what's under the hood of this bad boy?
Yeah, I thought you will never ask. We've been talking about the general market, and at some point I should talk about our Vision C5. So Vision C5, something that we publicly introduced in May at Embedded Vision System, and it is available for our customers today to integrate in the system. Vision C5 is a complete standalone DSP that runs all neural network. So it's not an accelerator. It's a general purpose and programmable DSP. So that's the number one point that I would like to make. The second point that I would make, it's scalable. We can scale into multi-teraMAC per second solution. And then the third thing is that with any DSP, you need very good software tools. Tensilica has been in the business of selling processor for over 17 years. So we have a very good software tools like compilers, assemblers, the simulators. And on top of it, we've been selling our imaging and vision DSP for last 5 years, and same tools chain and same tool sets will be used for Vision C5. So again, this is a proven and a very solid software tool sets that our customer can use with our Vision C5 DSP.
Okay, so Pulin, what does this really look like in an SoC?
Yeah, at the end of the day, when customers are making an SoC, they are looking for an IP that they can integrate very easily on the existing subsystem. And today, the interface that they would like to integrate it on is an AXI. So this IP sits on an AXI interface. The DSP is what we call a hardware architecture. So it has a dedicated data memory, and it has a dedicated instruction memory and an instruction cache. Also, it has an integrated IDMA to bring data from external memory to the local data memory. We provide an IP that fits, that can integrate very easily with associated memory to our customers.
So, Pulin, what does the processing power look like for this thing?
What we have done is that, as I described earlier, that the computational requirement for the neural network is tremendous. So we started out with a minimum 1 teraMAC processing power. So the way we do that is that it has 1024 8-bit MAC. So the DSP can do 1024 8-bit MAC in single cycle, but it can also do 512 16-bit MAC in single cycle. As I've been describing, this is a programmable machine. So it's actually a 4-way VLIW machine, and it's a SIMD 128-way 8-bit SIMD machine. We already talked about it's a complete DSP to run all neural network layer. But I think when we talk about computational capacity of 1000 MAC or 1000 teraMAC, you have to also say that does it have enough memory bandwidth? So it gives you the wide memory bandwidth of 1000 bit. It has an integrated DMA to bring the data from external DRAM. So what you're looking at is a very balanced architecture with tremendous tremendous computational capacity and tremendous memory bandwidth to make sure we can achieve very high performance for today's neural network or future neural networks.
Okay, so I know about neural networks a whole bunch, but my audience may not. Can you show me an example of what you mean by this typical neural network?
Yeah, so, this is a very simple form of a neural network that we have tried to describe over here. In a typical neural network, there's a convolution layer, which is the main computational requirement. And then it's usually followed by some kind of a normalization. And then you will do multiple times, and you hear this word called deep neural network. And what this means by that is like you might do this convolution layer followed by normalization layer like 150 times, so that's somebody call it deep, or somebody's mind 200 times might be a deep. The definition of deep may be different for different people, but doesn't matter. The point here is that in a neural network, you have convolution layer followed by a normalization layer. And after that, something called a fully connected layer followed by another normalization layer. So you just keep repeating this thing until you decide that now I have found my whatever you happen to be looking for. And what we are trying to say that this Vision C5 is designed to do all those things on itself. You don't need to say, okay, I'm going to do convolution layer on Vision C5 and then other layer somewhere else. No. Once you say, I have a neural network, you dedicated everything over here. That means all your other computational resources, whether it's your Vision DSP or your other main CPU or GPU, are free to do other tasks. You have a dedicated offload neural network DSP called Vision C5. That's what we are providing.
Okay, so Pulin, what if I have more than one processor in my design? Will C5 support multiprocessors?
Yeah, so we touched upon this thing earlier, that the computational requirement is increasing. And what we want to do is we architected this Vision C5 to provide a scalability. And this whole scalability concept is built into the Tensilica architecture for a long time. We have built this whole concept of shared memory architecture. We have something called interrupt and queue skewing, queues for synchronization, automated creation of multiprocessor system C models. So all these things we've been doing for over 17 years to do a multiprocessor design.
Nice.
And we brought the same thing to the Vision C5 to allow customers to do multiprocessor or and at the end that translates into multi-teraMAC design. So single Vision C5 gives you a 1 teraMAC, but if you put multiple of those, then that gives you multi-teraMAC design, and which is what you're going to need for future surveillance designs, future home design, future automotive design. So if I continue with these things, then the next slide over here that shows you that SoC diagram that I showed you here, you are looking at initial part a sensing system, a pre-processing system. And for the analysis now, here is an example where we have put multiple C5, but they are all sharing the data RAM. So this is one way of creating a multi-teraMAC system. If I kind of further expand this concept of multi-teraMAC, then the next slide over here shows you that there is no limit of how many Vision C5. You can put large number of Vision C5 to get to say 10 teraMAC or 20 teraMAC type of design that you may need for moving towards an autonomous concept. So what you saw that the architecture is designed to do multiprocessor. You could do a shared memory design. And then this last concept shows you that there is no limit in how many Vision C5 can be put to show a multi-teraMAC concept for any kind of future SoC that requires neural network processing.
Okay, so Pulin, what does the performance story look like here? How does this compare to, say, a GPU, for instance?
Yeah, anytime you introduce anything new like this, we have to show how we compare, because that's what we are selling to our customers. What we have done over here is a typical ImageNet neural network like AlexNet in Inception version 3, and we have compared to the commercially available GPU. So at the same frequency, 690 megahertz, Vision C5 will be up to 6x faster for AlexNet and up to 9x faster for Inception version 3 compared to the commercially available GPU.
Okay, so Pulin, what does the software flow look like here?
Yeah, so until now I've been talking about the DSP, and without a way to have creating a software, a DSP has no use.
Right.
So we have to think through that. So what is happening today that people are using commercially available framework called Caffe, TensorFlow, which is from Google, to train and create neural network. So if you have this neural network that you have generated, one needs a way to convert that into a code that they can run on Vision C5 DSP. And we provide what is called extensile neural network compiler, that basically a push button concept that you take the neural network description in Caffe or TensorFlow and convert a code to run on Vision C5. So within a very short time, you can find out that what is the performance of your neural network on our DSP. Either if you already have a hardware, you can test it out on your hardware, or you can test it out on our instruction set simulator and see how good it is. If you don't like it, you can go back and retrain it and go back and repeat this whole process. As I said, this is a very easy and a push button way of creating a code from a trained network done using this commercial level framework called Caffe and TensorFlow.
Okay, Pulin, can you give me a quick recap of your main points for me?
Cadence Tensilica announced Vision C5 DSP for neural network in May. It is available today. Our customers are already integrating this product. It is a complete standalone DSP IP core to run all neural network layers. The single core can provide you 1 teramex per second computational capacity in less than 1 millimeter square. It is general purpose and programmable to meet evolving requirements of this neural network market. It is optimized for a vision, radar, and fuse sensor application with high availability neural network computational need. It's architected for multi-teramark design to scale to multi-teramark solution, so no limit to number of Vision C5, and it's targeted at all these different markets: surveillance, automotive, drone, mobile, and home markets.
Well, fantastic. I think that's all I have time for today. Thank you so much for joining me, Pulin.
Thank you very much for taking time to talk to us.
And before we go, you didn't forget to click that link, did you? There you can find out more information about Vision C5 DSP for neural networks from Cadence Design Systems. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal or check out YouTube, keyword EE Journal.